Hi guys, so in this we will be looking at centripetal force and centripetal acceleration. Now, I want to remind you from normal kinematics that when an object accelerates, there's a change in velocity. We also defined acceleration as the rate of change of velocity. Okay, now if an object follows a circular path, even at a constant speed like we have in uniform circular motion, it still must be accelerating. Why? Because the direction of the velocity is changing. So for the direction of the velocity to change, there must be a force acting upon the object according to whose law? Newton's first law, which says that an object will continue its motion or will remain at rest unless a resultant force acts on it, a non-zero resultant force. Now, in the case of centripetal force and centripetal acceleration, both of them will be in the same direction. Why will they be in the same direction? Due to Newton's second law, which says that an object will accelerate in the direction of the resultant force. Okay, and this is what the textbook also says here, is that it will accelerate if it experiences a resultant force, and the acceleration will be in the same direction as the resultant force. So if we have that, then we must say that in the case of an object undergoing uniform circular motion, that the force that it experiences is constant, and therefore it experiences a constant acceleration as well. And in which direction is that force? Now, if you think of the example that I used in the previous lesson, where we had a bunch of keys tied to a string, and we now swirling that around, it's the tension in that string that is keeping the keys in the circular path. And that tension is actually drawing the keys inwards. So therefore, the direction of the force is towards the center of the rotation. Okay, and that is what centripetal means as well. It means seeking the center, towards the center. Okay, so we can now define centripetal acceleration and centripetal force as follows. Centripetal acceleration is defined as an acceleration that points towards the center of a circle, the center of rotation. We will use the symbol A with a subscript C to indicate that it's the centripetal acceleration. Our unit for acceleration is the same as previously. It's meters per second squared. And then our centripetal force is defined as the resultant force that acts toward a center of a circle and that causes centripetal acceleration. And the symbol here we will be using is FC, and as always, force is measured in the special unit of newtons. Now, this little box over here just gives you some information on what the word centripetal means. Like I said, it means center seeking or towards the center. Okay, and in other words, it's centripetal force and centripetal acceleration because both of them are directed towards the center of rotation. Okay, which then means, and this is really important that you remember this, is that the centripetal acceleration and centripetal force will always be perpendicular to the linear or tangential velocity. Okay, now it's important also to note here that centripetal force is not a type of force. It's rather a name that we give to a net force, because in the example of the keys that I'm swinging on a string, it's tension. That's my type of force. It's a tension force. Okay, so it can have various meanings, or it can be different types of forces, which the net result of is what we call the centripetal force. Okay, so in other words, because it's a net force, it can be a single force or it can be a combination of other forces. Now, what is the relationship between acceleration and velocity? Now, centripetal acceleration is directed towards the center of rotation that we said already, But how do we calculate it? What is the magnitude? The magnitude is equal to the linear velocity squared divided by the radius. Now, in terms of the units, how do we then get meters per second squared? Well, in other words, you've got meters per second that you square over there, which is going to be meters squared per second squared, and you divide that by meters. So in other words, you just have meters per second squared left, which is equal to the unit of acceleration. Okay, our linear velocity is in meters per second, and our radius is in meters. Okay, so these equations we can then combine with equation 55 so that we have centripetal acceleration in terms of angular velocity. And what we then get, because our linear velocity was equal to the angular velocity times the radius, we get that our centripetal acceleration is equal to our angular velocity squared times the radius. You can derive these formulae for yourself, and I would suggest that you do that and that you write it down so that you can see how the two relate. So if we then move on to centripetal force, now where do we get this equation? Now, very simply, and once again, I can only write with the highlighter, which is actually a bit frustrating to do. So we get the formula that the net force is equal to the mass times the acceleration. Now, acceleration in this case is our centripetal acceleration. So if it's our centripetal acceleration, which is equal to our linear velocity squared divided by the radius, and we times that with the mass, we get what we call our centripetal force. So once again, you can also derive this equation. And in terms of our units, our centripetal force will once again be in newtons, our mass will be in kilograms, our linear velocity is in meters per second, and our radius is in meters. Relating this equation again to our angular velocity, we can just replace our angular velocity into or our centripetal acceleration in terms of angular velocity into this equation to obtain this one over here. Now, you could rearrange these equations to make the radius the subject so that you get the radius as in terms of the centripetal force and the mass and the linear force. Now, from this equation, you can see a certain relationship that for a greater centripetal force, if the centripetal force increases, what will happen? We will have a smaller radius. Okay, so we will have a tighter curve. Now, I've assigned a simulation to you that also illustrates this truth that you can go and do. And it's not for marks or anything, it's just so that you can see the relationship between the radius and the centripetal force. Now, if you think of it, if I take my example of the key and the string again, and I would actually encourage you guys, play around with it physically at home. Take a piece of string tied to a bunch of keys or to a single key and start swinging it around. Okay? If you increase the force with which you are swinging it, what will happen? Yes, the angle might increase, but it will also rotate quicker. And because the angle increased, it actually means that if you go and look at the radius of the circular path, it would have decreased. It will have a smaller radius. Okay. Now, guys, it's really, really, really important that you understand that centripetal acceleration and linear acceleration is not the same thing. Remember, if we have uniform circular motion where the angular velocity, and it shouldn't be the angular velocity, it is also our linear velocity is constant. So both our angular velocity, the magnitude of that, because the angular velocity is actually changing all the time, the direction. So it's our linear velocity is constant. There is no linear acceleration. So the angular rotation is true as well, because you have a constant rate of rotation, so therefore you don't have any change in angular acceleration as well. You're not suddenly going over a certain part of the angle quicker and quicker and quicker. It remains the same, the rate with which that changes your angle versus time. So therefore your angular velocity is constant and you don't have angular acceleration. But remember, it's the directions that are changing of your centripetal acceleration and your centripetal force. And the direction of your linear velocity is also changing all the time. Okay, so in the next video, I will be discussing example 37.